Yeah, so yeah, yesterday we talked about spatial discrete probability distribution functions, and we discussed four such functions. One was just uniform, which is very, very simple. So one was uniform distribution. So which was like fx equal to 1 by. So whenever I'm writing here fx, so this is the PDF. Okay, this is the probability distribution function, which is probability of x equal to small x. So for uniform distribution, it is 1 by k, and x can take only finite value values. So x can take like x1, x2, xk. So there are k distinct data points, and for that, this probability correspond to each of this data point. It's, let's say, 1 by k. And then we talked about Bernoulli distribution. Bernoulli distribution, for which, okay, PP will also sometimes denote it as Bernoulli P, because P is the parameter here. So yes, so it is same thing as saying the probability distribution function of the Bernoulli distribution, or just the Bernoulli distribution. So this was P to the power x 1 minus P to the power 1 minus x, and x can take only two values, which is 0 and 1. So x belongs to 0 and 1. So, and we said x equal to 0 can be explained as a failure, and x equal to 1 as success. Then P here is the probability of success. So the parameter is like probability of success. And then we talked about binomial distribution. So, okay, so here we also introduced a concept called trial, or Bernoulli trial. Bernoulli trial. And then we talked about repeated Bernoulli trial, which gave us this binomial distribution. Binomial. So there are two parameters here in binomial distribution. One is n, and another one is just p. So some people write it like b n p. Okay, so this is the corresponding mass function, or the distribution function, which is ncx and p to the power x 1 minus p to the power 1 minus x, and x can take the value from 0, 1 up to n. So here we said, okay, n signifies number of Bernoulli trials, and this gives the probability that the probability of number of success x times. So x equal to 0 means no success, x equal to 1 means one success, okay, in n trials, and so on. And we also said that this is independent. This is very, very important. These trials are independent Bernoulli trials.
Sir?
And then, yeah.
Sir, it should be 1 minus p power n minus x, no, sir?
1 minus?
P in the
Oh,
binomial.
yeah. Sorry. Yeah, n minus x. Yes, you're right. Yeah, and then we talked about another distribution, which is called negative binomial distribution. So negative binomial distribution. So some people don't really like b bar, okay, b bar, and then here the parameter will change. Here it is k and x. Okay, here also you can write P, because P is also there. You can write P. And it was, okay, so this is Fx. This is Fx, okay, which is defined as this: x minus 1, ck minus 1, p to the power k, and 1 minus p to the power x minus k. And here x can take the value k, k plus 1, and so on, k plus 2, k plus 2, and so on. So essentially, we said this is the probability that you will have kth success in xth trial, where p is the probability of success. Okay, this distribution is also called, sometimes it is also called, I think, Pascal distribution. Okay, and also sometimes called, okay, let me just say this Pascal distribution. Okay, and once, okay, we also talked about like the means of these distributions and the variance of these distributions. Okay, so I gave you some formulas of means and variances, and if you want, you can just plot it. Okay, using any mathematical software in any programming language, you can just plot this for different values of xp and so on, and you can see how does it look like, the histogram, how does it look like. You can plot the histogram. Okay. Now, today we'll talk out first a special case of this binomial distribution, negative binomial distribution, which is called geometric distribution. So, geometric distribution is a special case. Okay, just the case is like just take k equal to 1, the first success. Okay, first success. This is what happens in xth trial. Okay, so k is the success here. K is the number of successes, and x is the trial number. Okay, on which trial you have that many k many success. Okay, so x is the number of trials. Okay, or index for the trial, or index for the trial, index for the trial. So if I observe the first success, then this distribution is called geometric distribution. So k equal to 1 in Pascal, or the negative binomial distribution. So in that case, then what happens? So sometimes it's like g, okay, gxp, geometric distribution. It will be just, if you take k equal to 1 there, it will be just p 1 minus p to the power x minus 1. So then x can be here, x can belong to 1, 2, 3, and so on. That means you can have the first success at the first trial, or first success at the second trial, first success at the third trial, and so on. So x denotes the same thing, the index of the trial. And k is the first success. So when you observe the first success, so this is the probability that you observe the first success, okay, at xth trial. Yeah, so these four are fundamental discrete probability distribution functions. And now I'll talk about a little complicated distribution function, and I'll tell you why it is little complicated. So this distribution is known as hypergeometric distribution. So now we'll talk about hypergeometric distribution. Okay, so okay, it is like related to binomial in some sense. We'll talk about why it is related to binomial and in which sense. But you can assume for the time being that in binomial distributions, okay, in binomial distribution, we talked about trials, okay, repeated trials, okay, which are independent. Here you can say that the trials, the first assumption, okay, assumption is the trials are
Sir,
not, yes.
sir, in the geometrical distribution, gx equal to the the success at x position, right?
So yeah, so when you, so this is, so if P here is the probability of success, then
Yes. So this is the
so
first
what is
success as x position.
yes, so if you just remember that picture which I had drawn yesterday, it is like 1 0 0, okay, or maybe 0 1 1 0, so on. Okay, so in general, so something like 0 1, yeah, it goes on like this. So something like here, so what happens to negative binomial, like here, so this is 1 2 3 4 5, so this is the second success in the fifth trial. Okay, this is fifth, sixth, seventh, eighth. This is the third success in the eighth trial, but this is the first success. Okay, now what I'm, suppose I don't know this, so this sequence is observed after you have all the trials. Okay, so once you have tossed the coin, let's say, okay, so then you have this one. But if you do not do that, what is the probability that you will have success at the first trial, success at the second trial, success at the third trial, and so on? Okay, so it is the probability of the first success. Okay, what is the probability that you'll have a success at the first trial, or first success at the second trial, or first success at the third trial, and so on?
Sir, why is this called geometric distribution? Like,
Yeah, that
what
is,
exactly
yeah.
are you trying
uh,
to do?
Yeah, that is a good question. So I also I thought I will ask you that. So any guess why it is called, why is it called geometric distribution? Is it related to geometric series or something? Okay, suppose, yeah, somebody wants to say something.
So maybe
Sir,
it
if
is
we
related to geometric mean.
sir, if we like expand this 1 minus p to the x minus 1, we'll get a kind of GP. Maybe I'm not right.
Okay, so yeah, so I mean it can have many explanations, but suppose you want to have, let's say, so here I am only talking about PMFs, okay, the probability mass functions. I did not talk about the cumulative probability mass function. Okay, cumulative means like you take up to certain values of x and then sum over x. Okay, so x equal to up to 10 or 15, whatever it is, you just sum it over, then you'll see a series, like, so x equal to 1 and then 2 and then 3 and so on, and then you'll find that it looks like a geometric series. That's what it is. Okay, or you can give other explanations also, it is not a problem.
Sir, can you
Okay,
explain this 0 1 0 0 1 0 0 1 part again? Like, how does this correspond to that 1 2 3 in x?
one, no, so okay, so this we discussed yesterday. So let's say what I'm doing is I am tossing a coin. Okay, I'm tossing a coin. So once I toss a coin, okay, I do not know what will happen, head or tail. Now, after I toss the coin, I observe that, suppose tail occurred. Okay, so tail I'm denoting it as 0. Next, again I'm tossing the coin, and suppose I observe that 1 occurs. Okay, I mean the head occurs, and then again I am doing. So I keep on doing this. Okay, then I'm supposed to get this kind of a sequence of zeros and ones. Right, this is what I'm supposed to get. But my question is that before you toss the coin and observe whether it is tail or head, because I may get a different sequence, right? If I do it for n times, let's say I do it for 100 times. Let's say, okay, this is 100 times. Suppose I get at the last. Let's say I do it for the 100 times. Okay, then I'll observe some sequence like this. And so in fact, how many possible sequences I can get, that will be 2 to the power 100, right? 2 to the power 100 sequences I'll get, because each position can have two possibilities. One is 0 and one is 1. Okay, so basically why it is 2 to the power 100, it will be like 0 1 to the power, I mean head and tail. 0 means, let's say, tail, and 1 means, let's say, head. Okay, to the
Yes,
power
sir.
100. Yeah,
Yes,
so
sir.
you'll
2
have
to the power 100.
2 to the power 100. Now the question is, yeah, now the question is, before I do that, my question is, before I do that, do this experiment and observe the possible outcomes, okay, after doing the experiment. My question is different. My question is, so here, once you do this toss, okay, then there is no probability, okay, right? You know everything, okay. Now, before I do that, before I do this experiment, now, so it is same thing as like, okay, I can give you another explanation for this. Let's say there are two balls here. Let's say there are one ball is like red ball, one ball is like white ball, something like it. You have different colors. So I need, basically, when I'm talking about Bernoulli trial, I have two distinct possibilities. Okay, so I am explaining that as a success and as a failure. So you have different balls here. Okay, so there are, let's say, 100 balls. Now you are picking these balls. Okay, once you pick that, so you get it, let's say, a red ball. So that may be a success, and let's say the other one is a failure. Then you do it for the second time. So this, you are doing it without replacing, okay? Without replacing, you are doing. So if you keep on doing that, the question will be, what is the probability that I'll get a red ball, okay? That will probability of success at the first trial. What is the probability that I'll get for, I'll get the red ball at the second trial? That means what is the probability that the success will occur first time in the second trial, and so on. So these probabilities are explained by, for example, using a geometric distribution. So because you are doing something, some experiment where outcomes are not deterministic, not certain, and there is a probability associated with the success. Success can be explained by anything, okay? I mean, anything depending on your experiment. And there are only two possibilities, okay? Success, one is success, another one is failure. Okay, so that is a Bernoulli trial only. First time when you are doing that is a Bernoulli trial. Second time also you are doing a Bernoulli trial, and first one is independent of the second one. Okay, so if you keep on doing that, okay, so my question will be, in the negative binomial, what was the probability? I mean, what is the probability that will have case success? Okay, let's say 100 heads. Okay, after maybe 200 or at the 200 trial. So the 200 time you are tossing the trees at that exactly at 200 time when you are tossing the coin. What is the probability that so it will appear head? Let's say. Okay, then that is the probability which is given by this formula. Is it okay now? So that's why it is K. That's what is K.
Trial is okay. So sir, in the formula you've written below g of x comma p, why haven't you put x minus 1 c k minus 1? And sir, why are we subtracting 1 from both? Let's say we have 100 coins and 50, we want to find the probability of 50 heads. So it will be 100c 50, no?
No, your coin is fixed because the probability of success is fixed. P is fixed.
Yes.
Coin is fixed. Now here I'm setting, so this was the probability which we discussed yesterday, okay, for kth success. So before the kth success, you had already k minus 1 success, okay, and the kth success you are getting it at the xth trial. That means you already beforehand you already had x minus 1 number of trials, and out of those x minus 1, you had k minus 1 success already.
Okay, got it.
Okay. Here I'm just putting k equal to 1. Okay, the first success. So it is the same thing. It is a special case of the negative binomial. Here I'm just setting, so here k number of successes. Okay, and here I just have the one success. So what is the probability that I will get first success? Okay, at the first trial or the second trial and so on. So that's why it is k equal to 1, 2, x equal to 1, 2, 3, and so on, because this is the number. It is the index for the trials, the number of trials. So that's why it is from k, starting from k to k plus 1 plus k plus 2 and so on, because I can have k success only at the kth trial, okay, or k plus 1th trial, or k plus 2 is a second 2 trial, and so on. But here my k is equal to 1, so that's why I have this, because the first success can occur at the first trial itself, or the second trial, or the third trial, and so on. Yeah, 1 minus p, why it is coming, it is very simple, because if it is not success, then it is a failure, right? So if suppose I'm getting the first success at the second trial, that means my first trial was a failure, it was not a success. And they are independent, so that's why this is the product. So the probability of an event, okay, where the events are independent events. So probability of A intersection B is probability of A times probability of B. So that's why this is. So when you say that you get the
Okay,
success at the second.
this is x minus 1 failures and then 1 success.
Yes. So because we are
Okay,
getting the
okay,
first success.
got it.
Okay.
Yes, sir.
Yeah. Okay. Yeah. So now we'll be talking about hypergeometric distribution. I'm saying that it has a connection with binomial distribution. Okay, and I'll talk about the connection a little later. But first, let me make an. So let me first recall that the binomial distribution, in the binomial distribution, we had independent Bernoulli trials. So all the coin toss was independent. Okay, so the outcome of the first trial, okay, for first toss is independent of the second one, and the outcome of the second one is independent of the outcome of the third trial. Our third toss is independent of first two tosses and so on. So they are all independent. So it is like that's picking something from the box independently. Okay. Now, so this is kind of like in binomial in some sense, the sampling is with replacement. Okay. Now, I'm sorry, without replacement. Now, what we are doing something here, which is with replacement. So here, my trials, let's say, are not independent. Okay. So they are dependent. Okay. Not independent. This is the first assumption. So because I told you that binomial distribution, when I said that we have independent Bernoulli trial, now we may have situations where they are dependent. Okay. So it is not independent. I'm not writing dependent because I do not know how it depends, right? So that's why I'm writing not independent. Okay, it depends on something. Okay, so okay, we'll see that. So here our first, so there are many parameters here in this distribution. First of all, consider you have a collection. Okay, consider a set or a collection of, let's say, capital N elements. Okay, like balls like this. Okay, like red and white balls or something like that. You have two different colors. And let's say, suppose, okay, M out of these N elements, okay, N elements are considered as success. Okay, that means if say there are two different kinds of colors of balls, then maybe this particular ball can be considered as a success. Okay, other one is then failure. So whenever I say M of them, capital M of them are success, that means N minus M are failure. Okay, which means N minus M are considered as failure. Okay, now what we are interested in, so this is my assumption first of all. Okay, now I'm asking the question, so what we are interested in, we are interested in the probability of getting X success in N trial. These two numbers are independent. I mean, in a sense, like this small n can be maximum capital N, okay? Because capital N is the number of elements, okay? So what we are interested in that I'll get X successes. That means let's say 2 success, 3 success. I mean, suppose you have, yeah. So suppose we have this bag of balls, okay? Now I keep on doing this without replacement. And what is the probability that if I pick, like if I do this process for 100 times, what is the probability that at the 100th time when I'm doing it, okay, I'll have, let's say, 15 successes or 55 successes, something like that. Yeah. So if I want to calculate that, so this is my question, okay? I'm interested in the probability of getting X successes in n trials, okay? Now, how do I do that? So I am interested only about success, okay? So how many ways I can get success, X number of success? See, now there are capital M number of successes. So that means, okay, how many ways I can get a success? I can get a success. So from the above information, from above, what we can say? From above, we have the following observations. Okay, we have the following observations. First of all, there are MC X, okay, ways of choosing X successes. X of the M successes. So now, in that case, if I do it for the n times, that I'll get X successes in n trials. That means n minus X. That was from the failure. And number of failures is n minus m. So n minus m c n minus x. This is the number of failures. This is the number of ways, okay, of choosing n minus x of the n minus m failures. So if that is the case, okay, then
Sir,
what
did we
is
do
the number of
n-
ways? Yes, please go ahead.
Why did we do n minus m?
This one.
Yes, sir.
Yeah. So if I obtain X successes, okay, F successes in n trials, that means small n minus X is the number of failures.
Yes, sir.
Okay. Now, what is the total number of failures I can have? This is n minus m. So then, because I had n elements, m of them are success. So n minus m are, of course, failures. Now, when I have small n minus x number of failures, that means
Yes,
those
sir.
failures should come
Sir,
from
I thought
n minus m.
Yes, sir. Yes, I got mistaken between m. So
Oh,
yes.
okay. So this is the number a, okay, number of ways of choosing n minus x failures, okay, or n minus x of the n minus m failures, okay. So what is the total number of ways of choosing x successes and n minus x failures? So I mean, if you consider this as an event, this as an event, then I'm talking about probability of intersection of these two events, okay. And then of course these are independent, so it is this times this, okay. So I can say thus mcx times n minus m cn minus x is that this is the number of ways okay, of x successes and n minus s failures. Okay, this is my first observation. Okay, this is observation 1. Now, what is
So,
my second observation?
can
Yes.
you please explain how are they independent?
Okay, because if success happens, failure will not happen, right? Independent in a sense, see, so independent in a sense that if this is the success, let's say, this many ways I can get a success, okay? So of course, then this many ways, then I'll get failure. And if I want to have both at the same time, that means this many ways success and this many ways failures, then that will be the product of that. Because A, B, so probability of A times B is equal to probability of A times probability of B. Now your question is why these are independent? Because if, I mean, this does not have any effect on this one. Because, I mean, what I'm trying to tell you is, this is the number of ways I mean, in that sense, this is the number of way of choosing this many successes. Then of course, then other side, I mean, whatever the remaining we have, this is the, I mean, this number has no effect on this number. This is what I'm trying to tell you. Because it is either success or failure. So if I already know that this is a possibility of successes, it has no effect on the remaining one. So then remaining one has to be failures.
Sir,
So then the assumption that they are not independent is, so we are following that by using NCX and not using the total probability.
I didn't get it. What is that you're saying? Please go ahead.
So in the normal case, if the assumption was not, if the trials were independent, then we could have chosen from, it would be like choosing with replacement. And in this case, it is without replacement. Is it correct, sir?
No. So yeah, this is no. So this entire thing is happening. So let me do it this way. Let me try to explain this way. So you have a here
Sir,
box
can you
here.
take an
Okay?
example and explain, like with numbers?
Yeah. So you can have a ball. Let's say here, 100 balls are there. Okay. But I need to now write 1, 2, 3 these balls. Okay. 4 is a particular type of balls, and this is like another kind of a ball. Let's say 1, 2, okay, 3, 4, and so on. Now you start picking the balls. Okay. Now let's say this represents success, and this represents failure. Some I here. Okay. And let's say some J here. Okay. IJ are like 1, 2, 3, 4. This is failure. Now, suppose you do it for the sake of simplicity, you do it 2 times. Okay. Or maybe 3 times. Okay. So now your question is, you want to do this, you want to pick the balls from here, n equal to 3 times. Okay. Now the question is, I'm interested in this x when this x is 2. That 2 times you get success. Okay. Now, if that is going to happen, that you have 2 successes out of 3 trials. Now, when you pick this 2 trials, meaning you can have either this, like let's say, either you have success. What is that? Success is this. So either you have this or you have this. I'm not indexing it right now. Okay. You can have this. Okay. And so on. These are the possibilities you can have. Okay. Now, this ball, okay, this ball, which is a failure, can be one of these 4 balls. 1, 2, 3, 4. 1, 2, 3, 4. This ball, whenever you are doing it, this can happen. And for example, let us focus on this one, that this has happened. And what I'm saying is, this is success, but these balls could be the first and the second ball, or the first and the third ball, or first and the fourth ball, or the second or the fourth ball, all these possibilities. Now this remaining part is independent of this, because this remaining part is one failure. Okay, one failure. This ball can be the first ball, second ball, third ball, or fourth ball. So whenever you have this fact that you have already, I'm fixing this, that suppose first time when you take out one ball, you got this round one, and for other 2, the next 2 tiles, you got the square one. Now once you get the square one, how many ways you can get the square ones? That is independent of how many ways you can get this red one, round one. This is what I'm saying here.
sir.
Other thing is,
Sir,
yeah.
but didn't we assume that the trials are not independent?
Yes, but now see here, not independent meaning, say these 2 balls, these 2 square balls, okay. So let me do it this way. I'm giving you one example, okay. So let me fix my example.
Sir, can we say that the
Yeah.
trial are dependent? That's why we are taking n,
No,
like
no,
n minus nc, n minus x.
Wait. See, the trials meaning I keep the ball and I am not putting it back again. Okay. I'm keeping the ball. So okay, let me just say this. Suppose I have this situation. Okay, 3 times I am doing this. Okay, 3 times I am doing this trial. Now I have this situation. This is the first time it was a failure, and then second time it was a success, and now third time it was a success. So number of success here, success is equal to 2. Okay, and number of failure is equal to 1. Now here what I'm saying. Now when I'm having this success, this is the number of ways of choosing X of M successes. Now say here, how many successes I can have? I can have 4 successes. Okay, that means this 2, this square one and this one can be 2 of this 4.
4C2.
But yes, 4C2. So that is what my question is. Now this could be 1, 2, the first this square ball and the second ball, or the same thing. It could be, let's say this one, let's say the second and third one, let's say, and keep on. I mean, you have all those possibilities. See, this possibilities is independent of this possibility. Now, when you are having, so if you just forget about this part for the time being.
So sir,
what
you mean ki, like the success and failure are independent, but in a series of trial, I mean in a single trial, or in a single event that we make, if we make certain trials, then those are not independent.
Can you repeat it again? I didn't get the last point.
Okay, so suppose we consider an event of 4 trials. Okay.
Yes.
So in that 4 trials, the events are not independent. But if we consider these outcomes that you have highlighted, then these are independent.
Yeah. So highlighted here means this choice of this coin. It's not the coin, but the ball. So I am only interested about the number of successes. I mean, let's say the number of balls. So that I am here, I am getting two balls. Okay, but which one of these balls? That I'm let's say not interested. But how many ways I can have this then?
Yes, sir.
First,
Got it.
Okay,
So,
now it's clear, sir.
sir,
okay, clear.
why aren't we multiplying by 3 factorial? So if we have 3 options, once we choose all of our objects, then we should permute them in different ways. So why aren't we
Yes. Yeah. So here I'm multiplying that. So this is what I'm doing here. So this will give me the entire thing. This is the number of ways of X success and N minus 1 failure. This is first I calculate number of success.
Into number of and the ways of choosing failures, but now we should multiply by n factorial, right? Because let's look at the example which you gave. So इसमें आपने from the 4 squares you chose 2 of them, and then from the circle you chose 1 of them. So the total ways to choose 2 squares and 1 circle from the objects in the bag is 4C2 into 4C1. And now there, for every choice of the objects, we have their 3 factorial permutations. So we should multiply by 3 factorial, right?
No. See one thing. No. What we are mixing is, so this is, I am fixing a pattern. This is my pattern. Okay. I'm not getting anything else. But see, in this particular pattern, the second 2 ball, you have this thing when I'm numbering the balls. But this now, this could be 1, this could be 2, this could be 3. Just a minute. And then this also could be 1.
Fixed the pattern. I've understood that, but why can't the pattern vary? Why does the circle have to come first? Why can't the square come first?
Yeah, that is what I'm saying. If we fix, so that's why earlier I think okay, no, I deleted it. So the thing is, I am only interested about number of balls, okay? But this may come this way. I'm fixing this pattern first of all, okay? Let's say it is the case, but it can be different. So it can be this one, and this one, because I'm not interested how it appeared. I'm only interested about the number of success. I'm not interested about how how many, I mean, what is the pattern of successes? I'm not interested in that. I'm only interested about the number of success. I'm not interested about whether my first success occurred this
Yes,
one and second also success.
that's exactly why I'm saying we should multiply by 3 factorial. If you fix the pattern, then we don't need to multiply. But if the pattern can be varied, then we should multiply by the 3 factorial, assuming the objects are unique.
I don't get it, what you are saying.
Sir, let's say you chose circle number 1, and then you chose square number 1, and then you chose square number 2. Now, square number 1 can come before square number 2. So, one of the arrangements can be, so the first one you've drawn, circle 1, square 2. That's the first row which you've written. The second row can be circle 1, square 2, and then square 1, right? And then
Yeah, go
another
ahead.
one, then another one can be square 1, circle 1, square 2. So these are, all of these objects are the same, right? But we are taking different permutations of them. So that's what I'm asking, that shouldn't we permute them if you want to find the total ways they can be, they can
No, I'm
occur?
not interested. No, I'm
Okay.
not interested about total ways. I'm interested only about counting the how many balls, how many success. How it is obtained, I'm not interested.
So, sir, basically, can we say for every experiment there is a different ball, like there are different balls?
Every experiment different ball means?
Like, sir, if we select if we select 1 1 2 then we can now select 1 2 1. Like, if we take,
Maybe you are thinking this very complicated way. This is very, very simple. So what I'm
So you
doing
can
is,
move ahead.
yeah.
Then we will lose time, sir.
Okay. Yeah.
Maybe
So
if you explain further, we will understand, sir. There are some complications, but if you explain further, we will understand, sir.
okay. So yeah, I'm already running late corresponding to other sections. Yeah. So okay, let us assume for the timing that this is true. Okay. So this is the number of ways. How many? I mean, this is the number of ways you can obtain x successes and n minus x failures. Okay, from all the balls whatever you have, capital number of balls. Okay. Now, how many ways? Suppose if I just say, so yeah, so how many ways you can choose n balls? That is small n balls. So number of, yeah. So number of, I mean, I was not talking about ball, right? So number of choosing, or maybe how many trials you can have. I mean, what example I was giving, I also forgot. What did I write here? N was the number of, okay, elements I was saying, because I have to generalize this. I mean, ball is a particular example. Observation, this is that. So how many ways you can have, number of ways, okay, choosing n, okay, elements out of n elements, let's say it is ncn. So this is the number of total number of ways, okay, and so this is the number of way of choosing n out of n elements. This capital N is the number of elements, small is n is the number of elements you are choosing, okay. So then what can I say? That this is the number of ways I can choose n elements, and out of that, this is the number of ways that x successes and n minus x failures. So what is the probability? Then the probability. I mean, here I am assuming that all are equally likely. Okay. Probability of x success in trials is m cx n minus m Cn minus x divided by NCn. So from here, the hypergeometric distribution is exactly this one. So now I will define what is the hypergeometric distribution. So a random variable x is said to have hypergeometric distribution if fx, okay, if fx equal to, so x is here the number of successes, okay, out of n trials, small n trials, is mcx n minus mcn minus x and nc small n. Okay, now what are the where x can go? X can be from, x can be 1, 0, 1, 2, the number of success, okay, out of n trials. And of course, x will be less equal to m, capital M, because capital M is the number of successes maximum you can have. And of course, n minus x is also less equal to n minus n. Okay, now I have little time, so let us consider an example. Okay, this is an example. Okay, let's say what kind of example? Okay, let's say so in an air pollution, okay, in air pollution survey. So there is a survey about air pollution in trucks. Okay, air pollution survey. Okay, the inspector who is surveying this, okay, the inspector okay, decides to examine the exhaust of 6 of 24, let's say, trucks, okay, of a company. So a company has 24 trucks and the examiner decides to check 6 of them, okay, 24 trucks of a company. Okay, now if 4 of the company's trucks, 4 of the trucks, okay, 4 of the trucks emit, okay, excessive amounts of pollutants, what is the probability it is that none of the cars, okay, or none of the cars, none of the trucks will be included in the inspector sample. Okay, so there are 24 trucks, okay, of a company, and the examiner and the inspector, he decides to, let's say, examine exhaust of 6 of the trucks, okay, and let's say there are 4 trucks, okay, which actually have problems, meaning they release, let's say, excessive amounts of pollutants, okay, so they are the troubles. Now what is the probability that when the inspector, okay, choose the six trucks, none of these 4 trucks is included in the sample? This is a problem I want to solve. So this is a setup. So how do I go about it? And here you already know that you have to use, let's say, hypergeometric distribution.
Sir,
So then we have to Yeah, so just let me finish. So then here we have to decide first the values of these parameters. What are the parameters here? X is capital M, small n, small n. Capital M, capital M, small x, small n. Then I can find it out. So what is the probability? None of this. So the probability of success here is 0 here basically. None of this. None of the trucks will be included in the inspector samples. So none means the x should be equal to 0. Okay.
Means
So
all the trucks are the good. I mean, they are not emitting any pollutants, excessive
the
pollutants.
4 of them, except those 4, 4 of the trucks, okay, they emit success amounts of pollutants. Okay. So out of 24,
What does this sentence mean? The trucks will be included in the inspector sample. What does this mean?
inspector wants to examine only 6, right? So number of trials here actually is 6. Number of total trucks is, so here I had this ball example. So here I have these trucks. So these trucks, okay, so total number of trucks, let's say n is equal to 24. Okay. Now let's say there are 2 kinds of trucks. Okay. So 6 of them, 4 of them are the problematic. So 4 of them are, let's say, they emit excess amount of pollutants. Okay, 4 of them, and rest of them are in good condition, let's say. Now the examiner wants to pick 6 of them. Okay, so 6 times trial, let's say. Okay, 6 of them. Now, so now the question is, so let's say this. So n equal to 24. M here we are writing as 4 because my x is 0. X means what I'm writing x here. Probability of success means what? Success is 0 means picking the wrong ones, pick the wrong cars. Let's say now none of this x equal to 0 means no wrong car is chosen, wrong track is chosen. Okay, there are 4 such tracks which which are the problematic ones. Okay, so m equal to is total 4 actually here. Okay, the 4 are this circle ones. 4 are the circle ones. Okay. Now, what is the value of small n here? This is 6 number of trials. Okay. So then we can just find out the probability. So we have all the parameters and we can just put it in the formula and we can just find out this. So the thing is, so when we are discussing about a lot of distribution functions, so in an exam kind of a situation or in a realistic situation, you do not know. So you are given a problem to solve. Let's say, suppose you are in an industry, okay, where the deal, let's say hardware industry kind of a thing, okay, where you have to inspect something and do this, do that kind of a thing. So now the thing is, you do not know which kind of distribution, okay, you actually have to apply that will fit into your situation. Okay. So when the problem is given to you, from that problem, you have to decide the situation. Okay, because everything is discussed in terms of success and failure. So you have to choose success, you have to choose failures in such a way that will fit into your one of the distributions. Okay. For example, here, since we already know here that this will be hypergeometric, so we just need to fix these numbers, these parameters in this particular setup. But when you have all the possible distributions, then you have to choose, first of all, the distribution, which distribution that phenomena will fit in, and next the parameters which can explain that phenomena. That means the parameters of the corresponding distribution function. Okay, I think we have to stop here. If you have question, we can discuss for 5 minutes because, yeah. If you have question, we can discuss that. Yeah.
Sir, I had a
Sir,
question.